Good afternoon, dear participants of the conference. With your permission, I present a work on board hybrid neural network classifier of helicopter's turboshaft engine operational status. Helicopters, aircraft, turboshaft engines as recoverable objects during their service life require continuous monitoring, the complexity of which depends on the level of automation of obtaining, processing, storing, documenting information processes about their current state, the sequence and methods of which determine the monitoring information technology. Diagnostic of helicopters, aircraft, turboshaft engine operational status are necessary to match the strategy of its optimal control in the helicopter flight mode with object ratings. An analysis of work in the field of monitoring and diagnostic the helicopter's turboshaft engine operational status based on neural networks shows that such work is currently underway. However, due to a number of reasons, secrecy, narrow specialization of the task being solved, most publications lack engineering methods, and the existing ones are not adapted to aircraft engines of helicopters, as well as theoretical and practical recommendation for solving diagnostic problem. Therefore, the modernization of methods of neural network diagnostics of operational status of turboshaft engine is an urgent scientific and practical task. Let the state of turboshaft engine as an object of diagnostic be determined by the value of the vector of output parameters, the values of which can change in the event of emergency of critical situation in the operation of turboshaft engine. It is assumed that all its possible states can be divided into several areas, classes. The location of the state vector in the same region is defined as an event corresponding to the good state of turboshaft engine. With any of the possible failures of the elements assemblies in the operation of turboshaft engine, sudden or gradual, the vector of input parameters belong to one of the areas which is considered as an event associated with a failure state of the engine. The input parameters are turboshaft engine working process thermogas dynamic parameters present in this table, which are either recorded on board of the helicopter or calculation using a universal mathematical model of turboshaft engine. You can also see a description of the output diagnostic parameters. To adapt to the recognition of defects by a neural ensemble as part of the training sample, we distinguish 5 generalized classes of engine status. S0 serviceable reference status, S1 compressor defect, S2 combustion chamber defect, S3 compressor turbine defect, S4 free turbine defect, S5 exhaust unit defect. To solve the problem, a neural network classifier was developed based on an ensemble of neural network, which consists of radial basis network, RBF, perceptron, coherent network, and hybrid neural network. The architecture of the RBF network is a two-layer network in which the first layer performs a given nonlinear transformation without involving parameter tuning, so that the space of input is mapped to a new space. As a training algorithm for the RBF neural network, the modified training gradient. The perceptron neural network in the hybrid ensemble performed the function of the constant training field, combining the outputs of 6 neural networks of the RBF architecture with 3 outputs. Table shows a comparative analysis of the perceptron training results, on the basis of which the error backpropagation algorithm is selected as the perceptron training algorithm. Neural network Kohonen classifier. 3 inputs, 6 outputs. The network with a high degree of accuracy classifier recognized helicopter's turboshaft engine operational status, including taking into account the partial or complete uncertainty of its parameters. The results of training process of Kohonen neural network are presented in table. The developed hybrid training algorithm for a hybrid neural network is based on the backpropagation algorithm. Block diagram of the developed hybrid training algorithm for hybrid neural network is shown in figure. Information of the blocks of which is given in table. Also already note, the final stage of diagnostics is the decision making on the type of failure in helicopter turboshaft engine based on the analysis of the numerical vector. Thus, the graphical interpretation of the task is modified to the form shown in figure, where the cube vertices correspond to the center of clusters. Reference engine states, that is, S0, center of the cluster, precedent corresponding to the serviceable reference engine status. S1, center of the cluster corresponding to a defect in the compressor. S2, cluster center corresponding to a defect in combustion chamber. S3, center of the cluster corresponding to a defect in the compressor turbine. S4, cluster center corresponding to a defect in a free turbine. S5, cluster center corresponding to a defect in the S-out unit. Thus, the graphical interpretation of the task is modified to the form shown in figure. The results of testing unknown condition of helicopter's turboshaft engine on example of the TV3117 engine, which is a part of the power plant of the Mi-8 MTV helicopter, using the developed new neural network classifier, are presented in table. In this table, you see the results of a comparative analysis of the accuracy and error in diagnostic defect in helicopter's turboshaft engine units on example of defects in the compressor and compressor turbine. This figure shows the results of the efficiency of the neural network classifier for recognizing defects in helicopter's turboshaft engine, using, for example, of the TV3117 engine, fuel consumption, air temperature behind the compressor, gas temperature in front of the compressor turbine, gas generator rotor RPM and free turbine rotors, respectively, gas temperature behind the compressor turbine and free turbine, respectively. The results of a comparative analysis of the accuracy and error in diagnostic defect in helicopter's turboshaft engine units on the example of defects in the compressor and compressor turbine are given in table. Currently, several methods are known for parametric diagnostic of the gas turbine engine's operational status, which can be divided into methods. A. Method of diagnostic matrices. B. Method based on solving a system of normal equations. C. Method based on nonlinear optimization of a criterion characterizing the state of the engine. D. Method of adjustment using a square objective function. E. Method of adjustment using a modular objective function. The results of comparing the effectiveness of the neural network approach with methods A, B, C, D, and E show in this figure that the advantage of the developed neural network classifier over other methods increases as information about the controlled engine parameters decreases. The conclusions are presented on this slide. Thanks for attention.